left me right there.
And that's a Kansas.
Oh, that's it. Okay, I almost thought Pittsburgh. Okay, okay. Yeah, I'm not familiar with that. Yeah.
A very deceiving day.
Yes, yes. Okay. Hello?
Good morning.
Yeah. Just putting things together. 2 minutes.
Is the official start time of our class 9:30 or 9:35?
9:35.
Got it. Okay.
Yeah. Still I'm late, if that's the thing.
Yeah, that's what I was wondering.
Yeah. 9:35 usually. I was a little relaxed because I didn't know what exactly to do. I was not sure how much to do today. So.
Yeah. Morning, Luke.
Morning.
Rob here. Oh, out of this one. It's Rob. Do you guys see Rob? Or?
On Michael.
Oh yeah, Michael. Sorry. Yeah.
Okay.
Oh, this is the other class, right? Yeah. Sorry. Yeah. Bad. Yeah, I think Rob, Michael, and Luke, the three of you were new students, I suppose. Is that correct?
I think so. I think Luce is here.
Yeah, Luke. And oh yeah. Okay. So we're all of us now. 1, 2, 3, 4, 5, 6. I guess. Yeah.
So I have a question about the midterm.
Yes, and give me a second. Why is the audio not picking up? It's supposed to be up there. Okay, sound is good. Can you speak something again, Moses?
Yeah, I had a question about the midterm.
Yeah. Okay.
I just saw on D2L that it's due at 11:59 tonight, but I imagine that's incorrect since we discussed that we're doing a take home.
Yes, that is incorrect, and I'm supposed to change that because that was the plan earlier.
Mm-hmm.
Earlier, my point was that it will be in class, so I don't have to worry about when it is submitted. So I just gave it some random number. So if you could do me a favor, just can you send me one line saying that that's showing up wrong?
Yeah, sure. Okay.
I forget it completely, and then all of you guys will have problem submitting it.
Okay.
So thank you. This helps. Yeah. I should do that for 520 also. Yeah. Just one word is sufficient. So, yeah, we're all of us here. So we have, I did post the midterm. Please assume all of you guys at least give a look at it, if not gone through it. Unlike promised, I did not build anything on curvature. It's just too many things that are happening. So I couldn't come up with. So, but it's mostly on vector calculus, which we have already done. And wherever necessary, try not to go into XYZ coordinates and do the problem and come back. It will be longer, I presume. If you want, you can check it that way, but the expectation is that you work in the, if I ask you something in spherical or cylindrical coordinates, you do that in that coordinate system. That is the only, I would say, it's not a big restriction, but I expect you to do it that way, put it like that. I try not to say that you should do it in a certain way, especially if you want to check or something, go ahead and try it, but at least present your work in that language. Okay, and what else? And when it comes to curl of a vector, try not to use any standard results. For example, you have this determinant result usually for a curl. In XY coordinate system, it's okay, it is sort of trivial, but in a curvilinear coordinates, it is not obvious as to why that should be true. So avoid using the standard result. So do it explicitly. Whatever I'm asking, do it explicitly. Don't use any standard results. For example, in my notes, you might see the answer to some of the questions. So you cannot say that, oh, this is equal to the answer and not do the work. Okay, so show me the steps. That's the only requirement I put. Yeah, otherwise it's mostly vector calculus, slightly more than what you do in your math courses, but pretty much what you do in E&M, electromagnetism. This is all used very much. Okay, so that's what it is. Any questions in general?
When will it be due?
Before the next class, anytime before the next class. So 9:30 on Tuesday, let's say. But that doesn't mean that it is that long. I would say 3 of the problems should be easily doable in a classroom test with the thinking process and all that. So 5, I would say, with the thought process going, it should be 2 hours, I suppose. But often you make mistakes and it could be longer, I do understand. And it's just a perception. I didn't make the solution, so I don't know. Okay, so shall I teach something new, or do you guys want me to say something about this itself? Shall I start complex variables?
Sure.
Sure. Yeah. Just let's introduce complex variables in very simple form. Okay, and
excuse me, doctor.
yes.
Is it possible to, you mentioned it last time, is it possible to ask you about clarification of any section in the midterm during the office hours?
If I understood you correct, you would like to ask questions about the midterm in my office hours. Yes.
Yeah.
Try not to ask for the solution. Yeah, if there is a clarification or anything needed, or even if you say that I'm not able to proceed at all, then I can hint you to something. Okay, and maybe I should also at this stage say minimal interaction between you guys is okay. Minimal, let's keep it minimal. Usually in homework, I say you can do everything. Like you can look into your work, each other's work. You can look into anyone's work, take help from others. Here, you can talk about the question to each other, right? Even how did you begin? Let's say stick to words. Don't just have a healthy discussion. Don't say that show me your work, something like that. So is that, I mean, I know it's a vague statement, how far do you go? But so the point is I'm encouraging it, but at the same time, let's have the assessment also into picture and have a little bit. Okay, does that also help? Who was it? Rob had mentioned that you guys started a group, so feel free to do that. Is that, does this class also have it, or it's only that class?
I think it's only,
Oh, it's only that one.
I don't think anything was official.
right.
I think we were just kind of discussing the possibility of meeting outside of class.
I see.
And that was, I think, for the EMT. I don't know if that's for this course, but
So, do you guys want me to initiate something? Once I had tried the group me between for the class itself, I think that was last semester I tried, but there was no activity in that. There was zero activity in that, so I didn't see any point in that. But I can initiate that if you want. Or there is also this Zoom room that is available. We started it last semester again, but it was started in summer, but it was never used much.
yeah.
Do you guys think that will be good, useful?
Well, I'll send an email about that.
Yeah.
About the Zoom room, which I intended to do quite a bit earlier.
So how about this? Let me give some information on that. So there is a Zoom room. What is it called, by the way? I should know.
Well, it's this. Okay. Is it not the same link?
No, it will not be, because this is,
Okay.
I'm using the university account,
Got it.
but I have a private account on Zoom also. So that is the private account, and it has a different number. Zoom room is different. So a Zoom room will be provided by Ask Moses. Or I should be. Because I cannot look into this because this is not my usual. This is my university account. Let us go into other. Well, ask Moses or I will, or ask Moses or me, right? Why not? And the password is, I remember that. So this is, so go back then. So this is X, key is equal to IH. And somewhere it stops taking input, but I meant to say IH, but somewhere it stops. It doesn't take so many characters. So it is this up to whatever. So that's the Heisenberg commutation relation, so it's easy to remember.
I did find the meeting ID for that link.
Yes, please, go ahead.
Okay. It's 992-867-71838.
Did I do this double sizes correct?
Yep.
Yeah, so that should be accessible for anyone, anytime. So feel free to use it if you guys want to. It won't be recorded, so I won't. Or is it recorded? I'm not sure. I don't think it is recorded. Okay, so feel free to use it. So the point was that limited interaction is allowed. So, okay. Yeah, the only problem with Zoom room is that when you go there, no one might be there. Right? So, I don't know. So you'll have to have some communication before. So I don't know how you guys will manage. So. But yes, to answer the question again, Khaled, yes, you can always come to my office hours. And I'll try to help in a limited form without revealing too much. Right? Okay. Okay, so we want to do broadly what is called complex analysis, but let's begin with very simple thing, complex numbers. So what are complex numbers?
A real part and imaginary part.
Real part and imaginary part. Often when you take a square root operator, right? Sometimes you don't get a real number, so you extend your system to include you can say a combination of two real numbers. One is called the imaginary, and one is called the real. You can take it back all the way a little back just to give some. So that is natural numbers, right? So that is natural numbers. Whole numbers. What's the next step? Integers. And here it is 1, 2, 3, so on. And if you add 0 to this, that becomes a whole number. Integers is plus or minus 1. 0 plus or minus 1, plus or minus 2, plus or minus 3, and so on. And then comes rational numbers. Rational numbers are numbers that can be written as a fraction. So that's let's say m over n, where m and n are integers. And then there is irrational number. Rational number. How do you define an irrational number? We'll come to that. Yeah, how do you define an irrational number? And then so there's real numbers, correct? Anything else? What happens after real numbers? So that's a complex number, right? And what after complex numbers? Does anything happen after complex numbers? If you see this pattern, I'll try to give some thoughts on this.
What imaginary? That's part of.
No, that's part of the complex numbers. Yeah.
What was your question?
The question is, you see some pattern here, right? We are extending our number system. First there was 1, 2, 3, right? I think then the point is when you subtract 1 from 1 itself, there is the idea of 0 coming in, then you add a 0 to that, so that little bit of subtraction is taken care of. Then you see that, oh, I want more of subtraction possible, so then you build that integers. You're extending your number system, right? And then there is rational numbers, then you do irrational numbers, then comes real numbers. Each one is expanding in itself in a certain sense. Typically, you say this forms groups under algebra. So there is an algebra that obeys if you do pure mathematics. And then there are complex numbers, and the point is there anything beyond complex number, or is that the end of it?
Well, I was thinking of quaternions.
Yeah, very good. Yes. So that's quaternions. Right? Quaternions, since we are in physics, you're familiar with spin of a particle, right? In quantum mechanics, we talk about a spin, and often they're represented by matrices. Right, so complex numbers, if you want, so So Z is equal to, that is, let's call it A0 plus I times A1, right? So there is a 2, this is called the real part of the complex number, and this is called the imaginary part. Quaternions, let's call it, I think it's good to say H. So H is equal to A0 plus, instead of I, let's call it, since we are in physics, let's have this polyspin matrices, right? If you're not familiar, we'll talk about that later, not in the next few weeks. So this will be sigma 1, A1 plus sigma 2, A2 plus sigma 3, A3. In mathematics, usually you would say this is A0, or the way quaternions are typically defined is I times A1 plus J times A2 plus K times A3. So it's very much like your complex numbers, but there are 3 quantities and they don't commute. So this is like more like a cross product. So I times J, right, is K. And that is a cyclic rule that is followed. And if you interchange it, there's a negative sign. And then the properties associated with that, there is a lot of, this was developed by Hamilton in 1818. And again, it forms a closed algebra. If you do many operations, if you get back the number itself. What are quaternions?
Gotta be something.
Gotta be something, okay? Moses, since you said quaternions? Okay, so since it seems like, so there was 1, why not 2, right? There's no 2 in there, and that is the reason, yeah, that is special. In fact, when Hamilton tried it out, he was trying with 2. He was started doing it until here, and he struggled a lot. And suddenly it struck him that there is 3. And it turns out that this is not, the next one is not 3, you can have 8 of them. So it is called octonion.
That was going to be my guess.
Okay, yeah. Okay. And basically there are 8 of them instead of 3. So this is related to group theory. And then again, the question comes, what next, right? How far do you go? Like that, and Jordan might have said there must be something, but apparently it stops there. Okay, remarkably, we don't know, or in fact, if I'm not right, I don't understand this, but I'm told that it has been shown that you cannot have anything beyond this, at least in this form. You can build number systems in different other ways, but in this way of adding numbers, you cannot go beyond that is being shown. Okay, so that's just some popular stuff, and we want to do things in this space, like complex numbers. But before that, we want to talk about 2 interesting stuff. One is interesting properties, again, not at a rigorous level, but at least we should have a feel for what this means. One is countable set. So like, what does it mean to count something in a set, at least by definition? And the second is dense, and maybe ordered set. One is ordered set. Third is dense set. By countable, what I mean is I can actually count using these natural numbers. For example, whole numbers are countable. This is the first element, second element, third element, fourth element, and so on. Notice that the number itself doesn't have any name. This could be anything in that set. if I can associate a map, right, this, and so on, that means it is countable. And as far as you can do that, that also means that the number of elements in each one of them is the same. If you can find a one-to-one mapping from the natural numbers to any other set, one-to-one mapping, then that means that the number of elements in that is the same, even though both are infinite. Notice there is, it seems like there is an extra element here, but that's just a label. I just changed 1 to 0, 2 to 1, and so on. But since I cannot reach the end of this tail, I don't know how to figure out how far it goes. So for all practical purposes, this will be considered the same. And that's what it means by countable set. Any countable set has exactly the same number of elements as the natural number. So in that sense, these two sets are the same. In fact, these three sets have the same number of elements in that sense of counting. Even rational numbers, you can, or maybe I should ask, does rational numbers have more number of elements by any chance? One would think it has, because all these elements are discrete. Rational numbers is the first dense set you see. That means to say that give me any two rational numbers, I can get you a third rational number in between it, right? You just take the average, right? And you can keep doing that. And one would think that, oh, in that process, most probably this has more number of elements than that. But again, going by the first idea that if it is countable, then it should be the same. The idea is usually, at least one of the simplest ways of looking at it, or one of the obvious ways of looking at it, is that with some pattern you want to see, right? So this is 1, that's 2, that's 3, that's your M, let's say, and this is your N. And you want to have a pattern of going from one to the other, and there should be only one way of reaching the infinity, or you have to collect all the elements if you want. And at least if it was only on this side, you can see that there is a pattern. You can do this. Oh, maybe first I should say that these are all the rational numbers. Each point here represents a rational number, right? M and N. Like M over N is a label you attach to every point in there. And then you want to count this. Is it possible to linearly count these numbers? That's the idea we are talking about. It doesn't matter even if it was in the second quadrant, I first go here, and then my idea is that, okay, I should count this also. So then I'm counting this 4 times, do the other counting. So if you can come up with some pattern, even if it is just an idea, you don't have to write it as an expression, that's good enough. And then you say that that is countable. So in that sense, rational numbers, which is very counterintuitive, that rational numbers has the same number of elements in this sense of counting as natural numbers, right? It is like in the beginning, one intuitively speaking, it would be hard to grasp that, because one is dense and one is discrete, so one wouldn't expect it. So in that very hand waving, and at least the idea goes through it. So all these proofs get pretty detailed when you do it in a pure mathematics course, and we don't want to, or I don't want to get in that. It's just a motivation. Okay, and so the first number set that has more number of elements than anyone before that is actually the irrational numbers. Irrational numbers turns out that has more number of elements than before. So then we should try to at least have a feel for it. So what is an irrational numbers? So first think of a number line. So this requires the idea of a number line. That means to say that just draw a line geometrically and pick any point in there, and then ask, can that be written as M over N or not? and if it cannot be, or if it can be returned, then it's a rational number. If it cannot be returned, it's an irrational number. Right? So in that sense, it's not a defining statement. If it's not rational, and if it is part of a number line, then you say it's an irrational number. And it turns out that's also dense. Okay. So between every rational numbers, you can get an irrational number, and between any two irrational numbers, you can get irrational numbers. But then I said that this apparently has more number of elements than any of the ones earlier. So let me try to motivate that a little. So yeah, this can also be an extra credit. So I think this is a good thing to. So extra credit. And the extra credit is to look up, what is it called? It is associated with Cantor. I don't remember what it's called. Cantor's proof that irrational numbers has more number of elements than rational. Is that clear enough? But I'm going to show you a little bit of that, but I want you guys to anyway go over it and give a thought on it. So it's a kind of a nice thing to ponder about. So, so Cantor's argument is the following. So first, he assumes that every number in the irrational set can be mapped, right, to natural numbers. So you can basically list them. So let's take some number, right? So this is 3. So some random numbers, 1, 2, 3, and keep going, right? So there is a lot of numbers you can write there. And let's say this is 5.712. So you randomly list all the numbers in that's available to you in a row. Right? And this is 7.123, and so on. Right? So you randomly list all these numbers and keep doing that. So that's an infinite set there. And the question is, can we? Is this really? Can it be mapped to the natural number? So if we cannot map it, that means that's not. It has more number of elements. So his argument was simple. So let's start with this, and now switch this to 3. Take the first digit and switch to 2. Just if it is 1, make it 2. If it is 2, make it 3. If it is 4, make it the next number. And if it is 9, make it a 0, and so on. So this is 2, and keep everything else the same. So this number has changed. The first digit has changed. And the next number changed the second digit. Right, so that's 572,722. Right? And the next one changed. So this one, I changed the second one. Okay, this is the argument. So this is now 3 becomes 4. No, is that what I? No, I didn't mean that. Okay, sorry. I was thinking wrong. Okay, sorry. I didn't think again. Okay. So I construct a number by, since take the first number as 1. So let's say first one I'll write just 0. So this is 0. This is 2. I changed the first digit here. Right? Second digit, I start with 1 and then again change to 2. Third one, I start from here and make it 4. Let me write some more numbers, 8.5623, so on. Let's say 7, some random number 7. And this will be, fourth one will be 8. And I keep doing that forever. If you want, since there could be numbers on this side also, but since it is starting from natural numbers, it will always have some numbers to begin with, because first the assumption is that it can be actually written as a list. But this number now, the claim is it doesn't belong to this set. Why? Because it is not the first number, because the first is off. It is not the second number, because the second one is off. It's not the third number, because the third one is off. It's not the fourth, because fourth one is off. And you can keep going like this forever. So this number does not belong to this list. So we began with the argument that I can actually list all the irrational numbers. But then I created one more. So this one is not in that list, which means that I cannot list irrational numbers. It's a proof by contradiction in that sense. So it's a very, once you grasp it, it's a very straightforward idea, but crucial, and things were not the same since then, right? And this is remarkably very recent, like in 1880s or so. That's when this argument came up. And of course, real number is a number at any point on the number line is basically a real line, and complex numbers is a combination, right? Two real numbers. So there is a real number here and another real number there. And so then the question comes, why did someone build complex numbers? What was the need for that? Of course, once you see a complex number, there was motivation to build quaternions, and octonions can be something more like that. And it should be closed in itself. But first time to go from real to complex numbers, can you think of any motivation to do that? Square root is a good, usually the interpretation is that you wanted to take a square root of a negative number. But where did it show up? So, so historically, how this goes is that you wanted to find the cube roots of let's say, I think the equation is suppose you have x cubed plus px plus q is equal to 0. Is this solvable?
Yes.
Right. And is there a formula like quadratic formula or a cubic equation?
Yes.
That's correct. So you can have a accurate formula, and at least for cubic equations of this kind, notice that. So the point is, any cubic equation can be written in this form, right? Ax cubed plus bx squared plus cx plus d is equal to 0. So that's a general cubic equation. And it was already known by 1500s, 1550 and so on, that any cubic equation can be switched over to this. You can, just by moving the origin, switch from here to there. So the solution to cubic equation boils down to solutions to this equation. And first time this was realized was in what is called Cardano formula. And in there, it was noticed that if P and Q were numbers, like proper integers, even then, even though the roots itself, the cubic roots were real. So roots were real. But it couldn't be expressed in closed form. Like there was no expression for that unless you went into complex numbers. So they were real roots, but the numbers cannot be expressed in terms of real numbers itself, or they had to be added with two such numbers. So roots come up in plus or minus. So so you'll see an example. I don't think I'm clarifying this completely. I'll try to make a homework problem based on that, motivate where that history goes. And again, I would actually make this an extra credit. Look it up. This is a kind of a nice story, or dramatic story, I would say. In history, just look up Cardano formula, and you will see that there was a lot of rivalry between finding the solution for the cubic equation. And the story goes that there were two people. In those days, you didn't publish your result. Instead, you claimed that I have solved it, and you write it in a coded form, like we have encrypted encryptions here. So you will encrypt your solution and send a mail to someone else, and they cannot read it, saying that because you have encrypted it. But then that is a proof. Whenever you give the encryption, it is dated, and it is now your proprietary kind of thing. It's a way of patenting your thoughts. And in those days, if you could claim that you can solve a quadratic equation, then it is almost like a duel, like people compete with each other. And the story goes that one of them did not have a solution, but he claimed that I can solve it. And just because there was so much rivalry, overnight, the other person, because he said that, oh, it is solvable, he solved it. Right? Just because the other person said that he solved it, even though he never solved it actually. So that sort of gives you the psychology that once you know that there is a solution, then it becomes a little easier to solve it in a sense. And there's a lot of drama associated with that. So if you read I think it must be there in the wiki page, just a sort of dramatic thing. It also gives a thought on, so when you talk about square root of -4, right? So this is plus or minus 2i. So now we know that where I is equal to square root of -1, right? That's what we will talk in terms of. Then even now, if you're an experimental physicist, you would like to avoid that, right? I mean, what involves complex numbers? I mean, you can never measure a complex number. Why are we dealing with that? And that's true even during the early days of complex numbers. No one wanted to touch it. Like even though there were nice results available, no one wanted to deal with it. It was considered a dirty way of doing mathematics. You go out of your space and then you can get anything you want. It's like the way we treat infinities today, right? We don't know why things are working, but it seems like there seems to be some key in there, but it's not clean. Like it doesn't give a good feeling out there. So it is very similar. Complex numbers were treated as untouchable things until Euler started working with it. Euler was extremely reputed, and he started. But even then, that did not make it smooth. But then overnight, things changed once Gauss came and just made a statement publicly that complex numbers are okay. And overnight, it became complex numbers are perfectly well suited to work with. So that's kind of the way things go. No proof or anything happened. Or maybe I should be careful. A geometric picture came up. I think Argand diagram, we'll talk about that. Argand diagram. This came up in, I think, 1810s, maybe. Something around that, and Gauss was about a decade later. This gave a geometric picture of a complex number. Whatever we think of complex numbers as a real line and and an imaginary line, a two-dimensional plane on it. So that's basically what Argand diagram is. Just the geometric idea gave a lot of confidence in what was being done in complex numbers, and that led Gauss to make the statement that complex numbers are fine. And Cauchy came immediately afterwards, and he practically did everything in complex numbers. Every result that you know in complex numbers is done by Cauchy. I don't think he left anything straightforward remaining in 30 years or so. He's almost finished it off, or whatever was, at least whatever we see in the textbook stuff is there. So that's sort of the history of what we are going to deal with. And in many ways, like you might, if you have had some experience with real numbers and rational numbers, I'm not sure if you have felt it like that, often theorems and proofs and statements are easier in real numbers compared to discrete. So discrete physics is rather harder to deal with than continuous physics. Like differential equation is one thing. It's much more easier to do in continuous variable than a discrete variable. And in that sense, often complex numbers are much more richer and much more useful than real numbers, which is kind of counterintuitive. One would think that it is more complex, or it is at least has two variables in it. It is more complex, but it turns out there's a lot of richness in there than the real numbers, especially once we bring in the idea of calculus on complex numbers, and that's what we want to deal with. And that is Cauchy's contribution primarily, that how do you do calculus on complex numbers? And that's what we want to do, differentiation on a complex plane, integration on a complex plane, and those are the two important things we will deal with. So that's sort of history, simple motivation of what we are working on. So any questions or comments? Okay, since no questions, so let's say we are, so let's define a complex, so this is complex numbers. So complex numbers are paired real numbers, if you want. So we'll call this x plus I times y. So here a few things has to be said. X and y are real numbers. You can write that as belongs to the real set. And I is a symbol. It represents square root of -1. Right? And it has a property that I square, so I have to define the multiplication of I with I. That's what I square is, like multiplying two i's. Right? So I times I is I square. So that's equal to square root of -1 times square root of -1. Right? And what is that equal to? Square root of -1 times square root of -1?
Negative I.
Right, so it's negative I. Negative 1 even, right? So this is
I don't know why I said negative I.
yeah, I think you meant to say negative 1. Right? And there was an issue in this. Okay, is there something? Is that obvious? Something here. Give me a second. Yeah, I think this is okay. Yeah, I think so. I'm trying to think of that it's usually a catch. Okay, so this is multiplication, and I cube is equal to, you multiply 3 times, so this is minus I, and I raised to 4 is equal to plus 1. So start seeing a picture here. So that's pretty much our definition, right? It goes until here. So this is Z is equal to X plus IY. And often in questions, I don't take too much, I'm not very careful to say that which one is real and which one is imaginary. Most often in context, it is clear, but I try to write real variables as X and Y and Z as complex numbers. But again, that may not be always true. So usually in the context, it is clear. But if it's not clear, either ask me or yeah, don't assume too much. Okay, so that's Z. That's the definition in principle of complex number. And then we want to define as many operations we can with this. Right? So let's say there is addition and subtraction. That's the straightforward thing. Z1 is equal to X1 plus I times Y1. And Z2 is equal to X2 plus I times Y2. So there are 2 complex numbers now. And you would like to see what is the sum and difference. So if I want to add these 2 numbers, it's pretty much like adding 2 vectors, right? Usually we write vectors as x1 in the x hat direction plus y1 in the y hat direction, or I and a j. And now you have x2 in the x hat direction plus y2 in the y hat direction. And then you add these 2 and these 2. So it seems like complex numbers, you do exactly that. You add numbers that's there without the coefficient I. So that's sort of straight forward. If you're subtracting, you simply do the subtraction of these 2. So I is kind of saying that, okay, this is in vector. If you think of it as a vector, it's a component in that. But this is what is called is this is a so X is called here. Maybe I should say this. X is called the real part of it's represented as the real part of Z. RE means real part of the complex number, and Y is represented or called the imaginary part of Z. And pretty much like so since this has this connection with vectors, so you immediately think of it as a plane. So it seems like this has a nice diagrammatic feature. So now you say this is X, that's Y, and the complex. So this will be called, and this is basically a vector space, right? In a sense, and we will see the difference between the vector space and this. There's a lot of analogy in there. This will be called a complex plane, and sometimes we represent it like this, right? So Z, there's a Z plane, the real imaginary, and any complex number will be, so this is a complex number, so that's your x. That's your y. And if you want to add two numbers now, use the idea of vectors, correct? So this is one, so this is a complex number, z1. So that's your z1. And that is another complex number, z2. So let's say it could be randomly anywhere. It could be here. It's your z2. And then the question is, where is z1 plus z2? Use the idea of vectors, right? If these are vectors, then what you will do is you will make a parallelogram, correct? Idea of vectors in there, and wherever this crosses, so the parallelogram is just draw a line parallel to this, draw a line parallel to the first number, and the diagonal, if you want, is z1 plus z2. And z1 minus z2, when you want to subtract, it is equivalent to adding the negative of the other quantity. So flip z2 here, right? That's minus z2 if you want. And then you add these two quantities. And that is z1 minus z2, which is the same as this quantity here. And if this was the origin, that's the same thing. So that's your z1 minus z2. So that's a straightforward point. And then comes, before we proceed to multiplication and division, it is good to define what is called a conjugate operation, conjugate. So the goal is to do multiplication and division, but before that, let's define something called a conjugate of a complex number. And that will be for any complex number z, we will define the conjugate as z star. It depends on which book you're following or what notation it is. Sometimes people write to make it z bar. Right? Often I see, at least recently, what I've seen in mathematics is that they use z bar. So we will use z star. Right? So it's just a notation. And let me first write z so that it's clear what. So z is x plus iy, and z star will be if it is written as real and imaginary part already, then you just change the I sign of I. That is that x is real, y is real. So it's necessary to have it in that form. Sometimes you can also add two complex numbers. Right? So for example, be careful. So it's also true that so z is equal to z1 plus iz2. Right? So here the understanding is that z1 and z2 are complex numbers. This doesn't mean that z star is just changing. This is not that. So z star now would be, so let me write z1 is equal to x1 plus iy1, and z2 is equal to x2 plus iy2. So z star here will be z1 star minus I, so I change the sign, and z2 star. This is different from this, right? Because it was real, you don't have to worry about that stuff. And again, let's see that I'm assuming that you've seen some form of complex number before, at least at some elementary level. Okay. So that's a simple idea. Graphically, where the complex numbers. So again, we want to have a visual picture of a complex number. It's very useful. What is a real number? Every point on a straight line is a real number. That's an intuitive picture of it. You can make it more and more precise by making all the epsilons and deltas, but the idea is that every point on a straight line is a real number. Similarly, every point on a every point on a plane is a complex number. Right? Every point you can imagine in the plane, it extends to infinity. That's actually a complex number, except that it has some rules. When you add, it is exactly like vectors, but multiplication, we will see that there is a slight difference. Multiplication will not, is like when it comes to vector multiplication, we talk about dot product and cross products, right? Here, we will have an actual complex multiplication there. So if this is z, so that's your z, any arbitrary number. Where is z star? You basically make the negative quantity, right? So that's your z star. It seems like an arbitrary definition, but it plays a useful role when we are defining division. It is easier to define division after we have defined conjugate operation. So this is with the thought that we will define division very soon. Okay. So that's your conjugate operation, and now comes multiplication. Right? Multiplication and division, but let's first do multiplication. And multiplication of two complex numbers is as if we are doing normal multiplication. Distribution, everything goes through. So z1 times z2. Right? So this is the definition of multiplication is going to be x1 plus I y1 times x2 plus I times y2. And now I have to, from this point on, I pretend as if I'm doing normal multiplication, except that whenever there is an I have to use some rules. Right? So I distribute it like I usually do. All those should be Christian, but the point is that all that works through. So if you want, you can list all those rules that I can actually distribute them, associativity, and so on, commutativity, and so on. So this is x1 times x2. Right? When I multiply x1 times x2, then I can have x1 times I times y2. So notice I have not changed the order, but I will, again, the idea is that I actually commutes with the real numbers. This is I times y1 times x2, and then there is I times y1 times I times y2. Right? That's how you would do that. And numbers commute, correct? Yeah, this is a good extracted problem, right? So this is lookup. If I were to tell you that there are two quantities that do not commute, that means to say there are entities x and y minus y times x is not equal to 0, and then you say that examples are matrices, correct? Matrices are differential operator, but that's okay. We do that in quantum mechanics. But now here is what I want you guys to look up. Suppose I were to ask you, given xy plus yx, right, has to be equal to 0. Right? Yeah. Okay. What is such a number system? Okay, look up that. Okay. How would you build, or what would be the properties of such a number system? This comes up in advanced, very advanced quantum mechanics. when you want to work with electrons, basically the Dirac equation, electrons have this property. Some properties of electrons go with that feature. Okay. Should I be giving you? Yeah, look up. I think I should give some name, right? So these are called Grassmann numbers. Probably not heard of it. It's not very popular, but it's important. Has anyone heard of Grassmann numbers before? Okay. All right. Yeah, so it's just good to know. It's just a, I mean, what you call general knowledge. I won't be dealing with that. If you ever do advanced quantum mechanics, you will see that. So that just came up because we have. But the point is, yeah, I actually commutes with real numbers, even if it was matrices and all that, because they consist of real quantities. They commute. So this is basically, and you can move things around. So you have x1, x2, and there are two i's there, plus I squared times y1, y2. And the other terms, since I can move I, say I and x1, y2, plus x2, y1. Okay. And that's equal to x1, x2, because I squared is minus 1. Right. This is the real part of the product of two complex numbers. And this is the imaginary part. Okay, so that's your product of two complex numbers. If you notice, I did, it's pretty easy as far as you stick to your old rules. The only new things you have used is I squared. Whenever I square comes, make it a minus 1 and use the feature that it commutes with real numbers and so on. Right? That's the, so there is a set of rules that have gone through in that. So that's one thing you have to capture, right? There is usually a list of rules you build if you're doing it from the very scratch and carefully, but I'm not going through that. There is one thing that is nice in here. If I were to do Z1 times Z2 star instead, that's also a valid multiplication. I mean, it's this is the actual multiplication of two complex numbers, but I can talk about a quantity constructed out of Z1 and instead of Z2 multiply it with Z2 star. Right? And this basically changes the second quantity has a minus there. That is equivalent to saying that everywhere if I change the sign of y2, I can rewrite that answer right away. So this will be x1, x2 plus y1, y2. And plus I times y2, I change sign. So let me do Z2 star. Let me say Z1 star Z. It's not very different, so I'll change the sign of Y instead. I get this the same, and this one becomes x1 y2 minus x2 y1. And then you, in this way of writing, there is some nice feature in this. x1, x2 plus y1, y2, does it remind you of anything?
Yeah.
No? x1, x2, y1, y2.
Kind of like a dot product.
Yeah, dot product, right? If you had two vectors, x1, x2, and so suppose I were to think of two vectors, good. So let me say Ri is equal to xi in the I hat direction plus yi in the j hat direction. Right? That's it, two vectors in there. So it seems like this is R1 dotted with R2, right? In a sense. What about the imaginary part? Does that remind you of anything? Cross product, right? These are two-dimensional vectors. So this is the third component of this cross product, right? So it is two-dimensional, then the cross product comes out of the board. Good, and so this is nothing but R1 crossed with R2, but then that's a vector. I want to make it a scalar, so dotted with z hat. The third component of R1 cross R2. So that's useful, especially when you want to have a geometric picture of or geometric feel of a complex number set. That is very useful, and we will see how we are going to define differentiation and integration. This will have connections with curl and divergence that we talk about. Like usually in a vector space, we define a divergence and a curl, right? And you will see that there is information in that. So vector space is a very or a vector feature of the space is good to have, and we will come to that later. We will see these connections coming out more and more openly. Right? Okay, so that's multiplication, and then comes division. Right?
So what was wrong
Yes.
with sticking with Z1, Z2 star? Why did you choose to change it again?
Tell that again.
What was wrong with originally you wrote Z1, Z2?
Oh, yeah, if I write Z2 star, then this changes sign, right?
Mm-hmm.
Then I have to write a minus of that. It's okay, nothing wrong. I didn't want that minus sign. This is cleaner, that's all. Right, it's okay because it's the same cross product except that it comes out with a minus sign. But who cares? It's on the other side, like it's a matter of visualization. So it's okay. Oh, this is not I hat. I meant to write I here. Sorry. This is I. Sorry. Hopefully that was not confusing. There is a complex plane, but sort of we can imagine that there is some dot product construction there, cross product construction there. And it gets more beautiful when we are doing calculus. There's a lot of information in there. Or there's a lot of constraint in there. That's the way to put it. Defining derivative on a complex plane imposes significant amount of constraint on the function, unlike real numbers. Okay, division, last thing. So first, let's do a simple division. Of course, we would like in general to do Z1 over Z2, right? That's the goal. But instead of that, let's just define 1 over Z2. And we do this. What is 1 over Z2? It has this feel that what do you mean by dividing a vector, right? Typically, we don't divide a vector. We have a scalar product, but in vector space, we never divided things, right? So sort of that. So how we do this is, that's where the conjugate definition comes in. You multiply and divide. So again, there are lots of rules going in here, what is allowed and what is not allowed. So this is 1 over Z2. I multiply by a Z2 star and a Z2 star. Multiplying numerator and divide denominator by the same should be okay. And now what is Z2 times Z2 star? If you were to see this, that gives you if y2 was the same as y1 and x2 was the same as x1, the imaginary part goes away, right? So this goes to 0, so that's real, always real. This, if it is z1 times z1 star. So z2 times z2 star is real, always. That's the advantage of that conjugate definition. And so that makes this a real number. And we know how to divide real numbers. Right? And we will often, so this is often defined as a magnitude. So that's the way, that's the absolute value of a complex number squared. And that's real, and we know how to divide real numbers. So I have converted division of a complex number into division of a real number multiplied by Z2 star. So that means that this is equal to x2 over Z2 star. X2 is real minus I of y2 over Z2 star, or magnitude of Z2 square, sorry. This is real, and that's real. I know how to deal with this. Right. So 1 over Z2 is written in terms of two real numbers. So now I know, so this is a complex number. I know how to deal with that. So if I know that, then I can do Z1 over Z2. Z1 over Z2 will be equal to Z1 times Z2 star divided by magnitude of Z2 square. So a problem in division is converted into a problem in multiplication divided by a real number, so we know how to do that. And let's stop this. So this is the basic operations. We will start having geometric pictures of this. We want to see how multiplication and division. So next time we'll talk about what is organ diagram, where is basically the polar coordinate, polar representation of a vector organ diagram. But historically, it played a very big role. The moment this came, complex numbers became tractable. Until then, they had no confidence in what they were doing. The moment organ diagram came in, they were comfortable with it. But it's basically the polar coordinates in a two-dimensional plane is what is organ diagram. Exactly that. And we'll talk about that. Okay. On Tuesday. Any comments? Have you guys seen these things?
Yes.
So Michael, you have Jordan?
Yeah.
Moses?
The Argand diagrams?
Not organ, just multiplication and division of complex numbers. This is
Oh.
Yeah. Form. No?
Yeah, I don't know. I mean, I think I have. I don't know that I've seen it written out explicitly like this.
Okay.
So I have a question really quick.
Yes.
So when I'm just thinking like when you're multiplying terms of I, So like if you have I to the third power, it's equal to negative I. And then
Yes.
four terms later, you have I to the 7, right? And that's equal to
Yes.
negative I.
That's also, yes, I cube is the same as I raised to 7. Yeah.
I to the 11. So with that, does that mean, I guess, I to the negative 1 is equal to,
Yes, so I next to the negative 1 is pretty much 1 over I. Correct? One has to be careful about these things, okay? So, yeah, what is this equal to?
I think negative I, but
This is negative I, you would argue, correct? Yeah, it is negative I. Yeah, I think this is this has no
it's
no.
confusing to me.
So here is what I think is the important point. Yeah. So yeah, I think I to the negative 1 is, I think this is what else could it be? Or here is the point. Whenever you have a confusion, I have not done Argand diagram. Okay. If you don't mind, can you ask me this question again on Tuesday?
Yes.
Remember to ask me this question again, and I'll explain it more clearly, because Argand diagram answers that question. You might think that, oh, is that -1 +1? I mean, in this, it is clear. I think what is more important is what is square root of minus I? I think so. Or did we not do this before? Yeah, I think because there's a homework problem I built out of this. Okay, because the interesting part is, have you guys heard of Euler?
Yeah.
Right. So Euler was the most reputed, like most prolific mathematician in all time, sort of. So when he makes mistakes, it's kind of nice to point out, right? So Euler also made a mistake, so it's kind of a joke. So I think when he was dealing with complex numbers. Remember, Euler came before Argand diagram, so he didn't have this geometric intuition. So he made errors in this. I think it is this. I'm trying to remember. Suppose you have square root of -1 times square root of -1, right? One way to argue this is that, oh, this is I times I, that's equal to -1, correct? Very intuitively, if you say, naively, okay? We will do this. Argand diagram gives a rigor to that, that's the point. And another way is that I start again now, -1 times -1. You say that, oh, things inside the square root multiply, correct? So this is the same as -1 times -1, which is square root of +1. So first I do the product inside I do the operations inside the square root, and then take the square root. And then you're confused, which square root do I take, plus or -1? So there seems to be a confusion here. Even at this stage, maybe you can say, this is plus or -1, maybe this is +1. Okay, it's not very obvious what that is. And apparently, story is that Euler made an error in this. Okay, or Euler struggled with this. It's not, like he couldn't proceed with complex, and even though he used a lot of results, or he used to manage well. But if you're not sure, or if you're not studying, or if you don't have a geometric feel for it, then you get into these kind of operations and you're confused, right? But we'll clarify this in Argand diagram. Very much like, again, think of infinities. When we deal with infinities, often we don't have a picture of these days when we are working with this. Sometimes it works, sometimes it doesn't work because we don't know the rules, right? All the rules are not given to us clearly. So we know half of the rules, so we manage reasonably well, but many times we fail. It's sort of a similar situation before 1800s, that complex numbers were there almost for 200 years or 250 years or so, but no one wanted to use it. And suddenly Argand diagram came. There was a clear indication of what it means, and then suddenly there was a boom, and everything was done immediately. Like Kochi, in the next 40 years, finished everything. Sort of finished everything. So yeah, so when we come back to that, good question though, very good question, Arun. Yeah. So if something stumbled, or Euler was stumbled, there must be something in there. You have other classes, or do you teach today, maybe? Do you teach?
No, I taught yesterday.
Okay.
I usually do teach today, but it's online today.
Okay. And you have an office, right? Is that single occupancy, or do you share?
I have 2 desks, but I think it's only mine right now. Really nice to have somewhere to go between classes or go sit for a while.
Yeah, that's true. Yeah, when you're an undergraduate student, that luxury is not there, right? Then you have to run to the library or something. Okay.
Yeah.
Yes.
The cases are still on the rise on campus, huh?
Yes. Or isn't it on the campus? It is okay, right? It is off campus. It is increasing. Isn't that what it is?
So but the off-campus students, it's kind of weird how they explain it, but it's not like the off-campus students don't come to campus. It's just that they don't live on campus.
Of course. Yeah. So they have a way of defining off campus and on campus. So apparently, if you compare with last week's numbers, the on campus students have not increased. They're saying the same, 9.
Yeah.
Off campus has shot from 20 to 47.
Mm-hmm.
And faculties have decreased from 2 to 1. So probably.
Yeah, I'm guessing the first faculty that was sick is probably no longer sick with the
The active cases.
Yeah.
Yeah, hopefully. I think I was comparing with UIUC. They do a lot of testing. And they have 50,000 students, so they have 5 times more students than us.
Mm-hmm.
And they have about, at least when I checked, that was before I sent you guys the email when I took that decision. They had 800 cases. That's almost 1,000 students, active cases. So I think that's a good number to have. So 1,000 and 50,000. So probably there is a similar number in SIU. That's probably a good number to keep in mind, the percentage wise, because we don't do so many testing, so we may not be seeing everything. So yeah, I don't know. Don't ask me. You guys probably know better than.
I actually have a couple students in my classes that are quarantined.
I see. Yeah, similar things in my class also. Yeah. But yeah, I think we accommodate. That's the best we can do as instructors. Yeah. Okay.
Okay.
Yeah. Enjoy.
Thanks, guys.
Bye, Aliyah. Very quiet. The kids are not around.
Yeah, because my daughters by me.
Okay. Bye-bye.
Bye. Thank you.
Bye-bye.
Hello.
Bye. Bye.
Bye.
So thank you. See
Okay. Yeah, bye, Michael.
you next week.
Thank you. Yeah.